very hard to find a lax pair. In fact, I don't think there's a one-size-fits-all prescription.
Because once we can know Schrödinger equation, I can show this.
But never mind Schrödinger equation right now. I'm talking about classical system.
Because I don't know how to obtain this Dirac bracket in this in Hamilton classical mechanics.
Well, of course you cannot. You're missing two things together. One is a Poisson. I mean, one is. I'm really just trying to recast a set of Poisson bracket in terms of rewriting as a matrix. This has nothing to do with going from Dirac bracket, and it has nothing to do with quantization right now, a priori. Okay. I mean, I have not introduced H bar. I have not introduced certain conserved quantity has to be equal to integer of H bar. I have not done any of those. So, but yes, but the punchline here is really that generally, this set of matrix that which allow you to recast your Hamiltonian equation into, they are actually quite hard to find. So, in fact, like I'm saying the right thing, right, Sasaki-san? Yes. So there's actually, for those of you introduced an integrable system, you should try to talk to the Japanese gentleman at the back. He's actually he's a visiting professor from Yukawa Institute, Yu Sasaki, and he's a world expert on integrable system as well. So, but anyway, so I think I'm making a sorry, yeah. So
it is a matrix infinite or infinite?
No. Generally, they are finite dimensional. In fact, if they are
because in quantum mechanics, this must be.
But why are we talking about quantum mechanics?
Yes, so this is my question. Why can we do this okay, we can. I don't know how to sing it.
Okay, well. So anyway, in general, they are very hard to find those lax pairs. So in fact, I think we're given a mechanical system that every time a lax pair was found, that was actually represent a kind of big breakthrough, right? Like when Toda system was found and when collegial Moser system was found. But yeah, we'll get to that. So, but suppose, so right now, okay, so what's the implication? Okay, so what? So suppose we actually find out what the L and M actually are, and we know L and M are actually functions of P and Q, which are themselves function of time. Okay, hopefully it's clear. Then we can write down, we know the solution to, let's just call this Lax equation, yes. The solution to the Lax equation can actually be decomposed into the following form, that you basically can kind of well, it's not really diagonalizing, but you can write it, you can decompose your matrix L, which is now a function of T, into three components, and two of them are the same, inverse each other, and one is actually independent of time, depends on only the initial values of your dynamical system. And M is also related to this function T. So both G and L are really kind of matrices. And you can show this very easily just by substituting into the last equation. This indeed is a solution. Because the point is that, and for those of you who actually know a little bit about gauge theory, you should really view this as something like this. Okay? This is basically, what is it? What is this? This is basically a connection that with the zero, right? And basically precisely play the role of the gauge field here. So therefore, in fact, this solution for Lax equation is not unique. You can perform something called a gauge transformation in such a way that L is you can multiply the solution by another matrix S, and so both ways. Then also you can also do the same for the M. So it's equal. And this should kind of remind you that this is how basically a gauge field transforms when under gauge transformation. And L is precisely something transformed in the adjoint representation of the gauge group should transform.
What is
G is some function. Like the punchline is just that. You can rewrite it in a general form. You can re-express the solution to Lax equations into this way.
job is to find G or
Right, the job will be trying to find, well, I mean, a lot of the time the job is actually trying to find, to find G, and also sometimes actually to find S. Basically, you can imagine that you can reduce your equation to a much more manageable form. That since S is otherwise arbitrary. But if you can find a clever choice of S, you can reduce your equation to a much simpler.
So what is our last?
The question is we don't know right now. There's no one-size-fits-all recipe for finding what exactly L and M actually are. Yeah, but so a lot of time they actually come from. Sasaki-san, do you want to comment on this? Any intelligent thing to say about like what people can say about finding L and M?
It's always try and error.
Okay. And the intelligent like eyeballing.
So we first find L and M and we find G.
Yeah, I mean once you find L and M, basically you can rewrite it into this form. Actually, sorry, yeah, I mean it might be slightly confusing, but yes, I mean the ultimate goal is always find L and G. Sorry, L and M, okay? And generally they are very hard to find. But once you know them, then it's guaranteed that you can rewrite it into the following form. It's basically just by definition that if they want to satisfy the last equation, they can be decomposed into such a general expression. And you see something is very nice. You can already see it. Because this is a matrix, if you take a trace on the both sides, what do we know? This is cyclicity. The reason why I write it this way is take this side. Okay? So what does that mean? That means at any other time, it's actually equal to where you started from. And that's basically a hallmark of conserved quantities. And in fact, that's why I'm writing it like this. Okay. Yeah, I was just jumping ahead of myself right now, but yeah, okay, might as well just talk about it. So yeah, so basically that's the punchline. That the reason why writing it out in this equation is useful is precisely we know the general solution can be expressed as such. But that's almost by its construction that ensure that there's a conserved quantity exists in your dynamical system in their entries. Okay? So in fact, okay, well I keep this equation, so I just write down why this is good. So, as I was explaining just now, that so suppose today, if we have another function, actually we can be more general. In fact, there's another function I call it I, which again is a matrix value function, but it's a function of L. But it's invariant under the transformation I goes to G, T, I, GT minus 1. You see where this is going? That then we know that, for example, as a concrete example, that I could be, you know, the IN, I guess, could be a trace of n power of L, right? Which will be invariant just simply by the property of the, so sorry, I should say L goes to G. Okay? Yeah, if it's invariant under such a transformation, sorry. So, then therefore, we can easily show that if we consider the evolution of this, is simply given by, is simply given by Ni trace L minus 1 Lm equals to 0, right? By the property that the trace L commutator is actually, if OK commutator is actually 0. Or if you think about it hard enough, then you realize, well, so basically those are time dependent. And basically this statement is telling you that you can actually also decompose the function. Basically, sorry, no, one writing, sorry, my apologies. Start again. So what I'm trying to say is that basically the function IL actually exists. It's actually invariant on the transformation. L goes to GT L0G, or basically just generate L. Okay? So for example, like an example of such a function with a trace of the function L, then we can easily calculate its time evolution just simply by considering the commutator. And the trace of commutator is simply 0, and therefore I is actually conserved. So the punchline I want to get at is that if today you actually know about how to construct a lattice pair, basically a matrix L and M, from a dynamical system, you can almost get, you can basically get a set of conserved charges basically almost for free. Okay? But that's only half of the story, if you recall. So that's not quite enough to ensure the integrability. So you actually need another condition. So first, you need them to be conserved, of course. Then second, you need to have all these conserved charges to be actually commuting, Poisson commuting with each other. So this additional requirement tells you that you actually need to have a kind of extra constraint on the various components entering those lattice pair L and N. And this constraint we are going to talk about now. But is there any question about a lattice pair? I mean, or at least why they might be useful? Or once they exist, just don't ask me how systematically constructed, because that's unknown. Good. Okay. So basically, the condition for for the conserved charges which we constructed for Lax pair to commute is the existence of something called a R matrix on the phase space. So, and I think that's the last topic I'm going to talk about today. Okay, so R matrix. So our starting point is that suppose, so I just write the next pair here. As a reference. So suppose the next matrix L can be diagonalized. I.e., we can write L into the following form. So where lambda here actually are the diagonal matrix which was the basic values or eigenvalues of the Lax matrix lambda. Okay, so let me assume L is a n by n matrix, but n is otherwise kept to be fixed and arbitrary. So, okay, so we can write down a canonical basis for this n by n matrix, which basically a canonical basis denoted as Eij, and the entries will be KL. It's basically given by Ik JL. So you should really read I and J labeling different n by n matrix, and for each of the n by n matrix Eij, its entries are labeled by K and L, and the value is given by this. Okay? So, using this basis, and this actually will be used quite heavily like later when we consider Besser ansatz and all that. So we can expand L into those bases. Okay, so there are different entries. So basically, I'm talking about L11, L12, and L21. Then each of numbers or functions of P and Q multiply one of the bases. Then you can write it out. And there's entries in K and L. Okay. So basically, we would like to evaluate, so in order to ensure the commutativities of all those conserved charges, we would like to need to know the following: Ij, KL. Basically, why is this? So, to do this, let me introduce. So, how many of you have seen tensor products? How many of you have not seen tensor products? Raise your hand. Okay, fine. Seems like everyone's seen it. I did ask. Okay. So, I introduced some notation. And if you don't know about those notations, I mean, go to your nearest Wikipedia. So, this is So this is a unit matrix, and this is your matrix L. And this is simply given by ij, Lij, Eij, unit matrix. And I think it should be quite apparent. Now, because later on, okay, so for those of you who have seen spin chain in your various kind of solid state physics manipulation, is that each of those will be representing an operator acting on a particular lattice site later. So those are very common. Okay, so and those are just a basis matrix. So we will define, because I need to tell you what exactly this guy means. So what we are really doing is that we can define the Poisson bracket between the two different lax matrix, L1 and L2. So define Poisson bracket between L1 and L2 is basically given by the following, Ij then KL, and the Poisson bracket of each component Lij and LKL multiply simply now on a tensor product. Okay. So now I can get to the statement that basically, or the condition we need to impose on the component of a lax matrix in order to ensure the conserved charges we constructed are indeed commuting, hence the integrability and so on.
Sorry,
Yes?
So it seems like the original system is two-dimensional. Here, the degrees of freedom is n squared.
So that means some of them can be redundant.
Okay. So how to get rid of those redundancies?
I think that generally are done case by case. Yeah, and then besides that's what's hard about finding the explicit lax matrix. Yeah. I do hope I have something more educated to say. But you might take too long. So the statement because I think the aim, I mean, of course, as you can imagine, that if you actually look at the Babylon's book, that's like 600 pages long or something, and that's just about the classical integrable system alone. So there's no way, almost no way I'm basically covering like a chapter 2 of the book. But that's actually, I think, is to give a fair intro of some of the standard machinery that, by the standard notion, I wouldn't even say machinery, standard notion that people use when discussing the kind of integrability in the classical mechanics. That, of course, I have no time going to touch upon, like, Riemann surface or Riemann-Hilbert property and all this stuff. Yeah, too bad. But that's something for you to read. So, so the statement is that the commuting properties of the eigen value lambda k, which are actually, as you can imagine, are implicit function of the canonical variables p and q, is equivalent. And the point is that we know that if L then can be decomposed into something like U, like this, Okay? Then once we know the eigenvalue commute, then you can trivially show that all these conserved charges based on the traces are actually commuting, because now if you know the trace of L to the some power, it's basically lambda to the some power, which consists of just eigenvalues. Okay? So then now that's why we want to show the eigenvalue themselves commute. Then the rest are just trivial. Okay? So, but this statement is actually equivalent to the existence of a function called R12, or generally it's an R matrix on the phase space M, such a way that this Poisson bracket we write down here is equal to the matrix R12 L1 minus R21 L2. Okay? So I have 10 minutes to show this. So okay, the proof. So, I mean, I will go a bit fast right now, and I will try to go again in the discussion this afternoon a bit slower. Okay? So, if there are questions. So, proof. So, let's go the other way. Let's see what's the consequence. Okay? So, let us assume all the eigenvalues Poisson commutes. Okay, so i.e. Okay, so what's the consequence? Well, so by diagonal, so if we have an eigenvalue, then we can diagonalize our matrix L. Then we can rewrite our Poisson bracket into just simply plug that in. So there will be one U associated with each of the matrix. So lambda 1, U1 minus 1. But this 1 and 2 are really, they are not really that different, because that only tells you where it is in your tensor product. So this is equal to in the lecture. Right. So okay, so if we now using the associate, so those are really Poisson brackets that for all these components in your Lax matrix. So for those of you